First order difference equations can be used in our fisheries economics analysis. Let us see how. We are trying to do fish stock analysis where the fish population is likely to increase by 5% each generation. So it's about 5% increase in each generation that the population of the fish increases. However, a catch of 8,000 is also happening, due to which 8,000 fishes will be lost from each generation. And then if FP represents the size of the population, so this becomes the size of the population represented by FP, and this is for generation T. There can be multiple generations out of which T is represented, representing the current or the certain generation that can go indefinitely in the time, because time passes and a new generation will come as the time goes ahead. Now what we are required to do is to write the difference equation that expresses the ft in terms of ft minus 1. It means that we want to develop a difference equation here, and then we have to solve this difference equation with the given initial condition. And then we can also understand the type of the time path, if dynamically stable or not, oscillatory or not. So the first thing that we are going to do is to develop the first order difference equation. I have highlighted it in such a way that it becomes clear that the current fish stock is actually 100 plus 5% of the last year's fish stock, or in the last generation's fish stock, where 8,000 is deducted from the generation that we are dealing with, because the fishes are caught, that is 8,000 fishes are caught. So this is a very simple equation, that the current fish stock is equal to 100 plus 5% of the last year's fish stock minus the fish catch that is done. So this is the first order difference equation that we have developed. Now we can try to solve it as well to get its time path. For this, definitely we need to make it adjacent to the first order difference equation, in which we have plus 1 as the subscript here, along with the independent variable, which in this case is t, and this is t. So we have to convert this t minus 1 into t by adding this plus 1, and now you can see we have plus 1 here and we have t here, which is in a good form because it is directly comparable with the first order difference equation. So this is, so the value of a can be extracted here. As you can see, the value of a is 1 minus 1.05, and the value of c is a negative value, which we can see is extracted. And now the values are going to be substituted in this formula, which is applicable because a is not equal to minus 1, and this is the formula. We have highlighted the values that we are going to substitute in the next step. This is a, this is value of b, which is equal to minus a. We have substituted the value here, and now simplification leads us to this first order the time path of the first order difference equation. This is the first order difference equation that we developed, and now we can check its dynamic stability. That can be done simply by looking at the value of b in its absolute terms, and the value of b is in absolute terms 1.05, which is not less than 1, which means that it is not a convergent case. On the other side, its actual value is not less than 0. It means that it is non-oscillatory case. So in other words, we can say it is a divergent case where there is a pattern which is non-oscillatory in nature. So now we can come to the final form. This is the elaborated form. This is the whole complementary function and its coefficient, its exponential part, which becomes the cause of exponential decay as the time passes, and this is the equilibrium value which is required that we want to achieve it. And this is how it happens that the time part doesn't approach to equilibrium value as the time passes. As we can see in the diagram, this is the equilibrium value, and it is the time path in the blue color, and it is going away from the equilibrium. It is non-oscillatory as well because it is going below the equilibrium and it's not crossing the equilibrium even once. It is going in one direction, that is away from the equilibrium. Here on x-axis we have time variable, and here we can clearly see that there is divergence, and the divergence happens in a non-oscillatory fashion. So we have tried to understood an example from the fisheries economics, where we are trying to observe the fish stock, its changes over time, and this was the time path. This was the diagram as well. The nature of the time path, the formula for finding the time path, the first formula of the first order difference equations, and then this derivation of it by using the different values of a and c, and then their substitution. They all helped us to develop this solution, and this was the development. The first time we developed the first order difference equation explaining the phenomenon of the fish stock and its growth over time, as well as incorporating the loss of the fish due to catch in each generation. So this is how we can use first order difference equation in the analysis of fish stock. Thank you.